This is section 4.2. We're doing confidence intervals for a proportion. So we learned how to find a confidence interval by testing lots of plausible values. But that's an incredibly tedious process. No one wants to find confidence intervals that way. So what we're going to do is learn a faster, more theoretical approach. Before we can learn that approach, let's review our central limit theorem. So you'll find we just keep reviewing this over and over. Okay, so our central limit theorem told us that the sampling distribution, so sampling distribution just tells you like all the possible sample proportions, so like all the possible sample proportions. Well, we can always say three things about that. We can tell you that the shape will be normal if you have at least 10 successes and 10 failures in each sample for proportions. The mean of all the possible p hats, which is right, mean of the p hats, is going to be equal to pi. The standard deviation of all the possible p hats will be the standard deviation of p hat. And we just have this new notation that we introduced in the last section. It just means the standard deviation of all the p hats, all the sample proportions. That's going to be equal to the square root of pi times 1 minus pi over n. Okay. Sometimes we can think of the standard deviation p hat, the standard deviation of all the possible p hats, as our sample-to-sample variability. It's measuring how much does my sample mean change from sample to sample. So let's pause and write that. I apologize, I think I said sample mean, but we're talking about proportions right now. So the standard deviation p hat, that's the standard deviation of all the different possible p hats, or is how much our sample proportion changes from sample to sample, because every different sample gives me a different sample proportion. Okay, so to keep reviewing, remember our empirical rule says if we have a symmetric data set that looks like a normal curve, then about 68% of our observations are within one standard deviation of the average, and about 95% of the observations are within 2 standard deviations, and 9.7 are within 3 standard deviations of the average. So what that means is if we're going to look at a sampling distribution of our possible sample proportions, and we like this 2 standard deviations and 95%, that's the one we use the most in this class. So we know about if this is the center, this is pi, our population proportion, then 95% of all the possible sample proportions are going to be within that 2 standard deviations. And that's really important to us. So let's try an example to see how we could use that. So USU has 28,000 students. We know that about 11% of all the USU students are graduate students. Now when I read that 11% of all, that tells me that's a population proportion. It's not a sample, it's a population proportion because it said all. Okay, so I could say that pi equals 0.11. If we were to take a sample of 200 USU students, so we'll say we want to take a sample size 200, what would we expect the sampling distribution of all the possible sample proportions to look like? Okay, well, first of all, when we look at possible sample proportions, it should be normal if we have at least 10 successes and 10 failures. Now, in this case, we haven't actually taken a sample yet. So do you know how many successes and failures you have? You don't actually know for sure how many successes and failures you have, but you can see how many you expect to get. So like we would expect 11% or 0.11 times 200. Let me see what that is. We'd expect about 22 successes. And then if there's 200 total, so 200 minus 22 should give me 178 failures. So that's what we expect. We haven't actually taken a sample, but we'd expect about 22 successes, 178 failures. That is big enough, so our shape should be normal. Okay, let's see, what would be the center or the mean of all the possible sample proportions I could get? Well, it will just be centered at pi, our population proportion. So in our case, that's just going to be 0.11. So we'd expect all possible sample proportions to be centered at 0.11. And the standard deviation of all the possible sample proportions, the SCP hat, let's see, that'll be the square root. Pi is 0.11, and then we have to times it by 1 minus 0.11 over our sample size of 200. When you put this into your calculator, do the 0.11 times 1 minus 0.11 first. Hit enter. Then divide by 200, enter, and then when you're done, take the square root of all of that. So you should get 0.02212. So that's the standard deviation of all those possible sample proportions. Please pause the video. Make sure you can actually put that into your calculator correctly. Now, I also gave you the simulated sampling distribution if I did it 10,000 times. So notice it does look normal. The mean matches what I calculated. The SC matches what I calculated. So these formulas let us know what the sampling distribution will look like before we ever actually do a simulation. Now, number 1 here says 95% of our possible sample proportion should be within what interval? So remember we said up above when we looked at the empirical rule, and this is why we looked at the empirical rule, okay, we said 95% of the possible sample proportion should be within pi plus or minus 2 standard deviations. So it should be within pi plus or minus 2 standard deviations. Okay. And so we'd have 0.11 plus or minus 2 times the standard deviations, which was 0.022. Let's see, so 0.11 minus 2 times 0.022. So you do the minus first. So you do 0.11 minus the 2 times that. So you get 0.0662. And then if I do 0.11 plus everything, I get 0.154. So I can tell you that 95% of the possible sample proportions should be between 0.066 and 0.154. So it would be from about here to here. I'm not like super on scale, but that would be about 95% of all the possible sample proportions. Okay. Now that's important because if 95% of all the possible sample proportions, the p-hats, are within 2 standard deviations of pi, could you reverse that? Could you then say that pi is within 2 standard deviations of 95% of the sample proportions? Or if I pick this sample proportion right here, so here's pi, okay, is pi within 2 standard deviations of this sample proportion? Yes. Is it within 2 standard deviations of this sample proportion? Yes. Within 2 standard deviations of that sample proportion? Yes. Is it within 2 standard deviations of this one? Well, no, that one's farther away. It's not going to be within 2 standard deviations. But most of these sample proportions are going to be within 2 standard deviations of pi. The reason that's important to us is we don't usually know what pi is, but we can find a sample proportion. We don't know our population proportion, but we can find a sample proportion. So if you didn't know that it was right there at pi, and you just pick a sample proportion, let's say this is your sample proportion, and you go out 2 standard deviations, that should include pi. So this way we change our here. So what we're going to do is we're going to pick a sample proportion and go out 2 standard deviations, and that sample proportion will probably include pi. We won't know for sure if it includes our population proportion, but it will probably include our population proportion. So let's look at part 3 here. Suppose we didn't know the USU had 11% graduate students, so we don't know our population proportion. If we took a sample and we got a sample proportion of 0.10, so can you find a 95% confidence interval for plausible values of pi? Well, let's think about this. If we didn't know that it was centered right there at, again, pi, but we know that we got 0.10, could we just go out 2 standard deviations to see how far out we are? Well, let's see, what do we get if we do, instead of centering at our population parameter, what if we try and center it at our sample proportion? So we'll take our sample proportion and plus or minus 2 standard deviations. Okay. So our p-hat, our sample proportion is, oh, sorry, I wrote that on the wrong spot. So I wrote on the wrong spot, but maybe it'll be helpful here. So we said if 95% of all the possible sample proportions are within 2 standard deviations of pi, we can say that pi is within 2 standard deviations of 95% of the p-hats. Or you can say that p-hat plus or minus 2 standard deviation will probably contain our population parameter pi. So let's figure out what it is for number 3 here. If our sample proportion is 0.10, we'll do 0.10 plus or minus 2 times our standard deviation of p-hat. So the standard deviation, let's use the one that we already calculated, and then we'll talk later about like how we could find this. Okay, but we'll use the one we already calculated, 0.022, just to save some time here while we're still learning. So I'll do 0.10 minus 2 times 0.022. Okay, so that gives me 0.0562, and then I'll add it instead, 0.144. So this interval, okay, is based off of my sample proportion. What I'm doing is I'm hoping that I got a sample proportion that was kind of in the middle so that when I go out those two standard deviations, it will actually cover pi. And in this case, does it contain our true value of pi of 0.11? Yes, it did contain 0.11. Let's see, what if another person took a sample of 200 students and found a sample proportion of 0.15? Let's find their 95% confidence interval. So they would do 0.15 plus or minus 2 standard deviations, so standard deviation being 0.022. So let's see what that gives me. So 0.15 minus 2 times 0.022 gives me 0.1062, and if I add it instead, I get 0.194. Okay. So the first time we had a sample proportion of 0.10, and let me erase all these and change my colors again. So when I had a sample proportion of 0.10, I come up to my sample proportion, I go out like 2 standard deviations, and look, my interval contains the population parameter pi. Now if I had a different sample proportion at 0.15, that means I'm actually starting like over here, and then I go out 2 standard deviations in either direction. But look, does it still contain my population parameter pi? Yes, it does. Okay. So when you look at the interval, 0.11 is in that interval. I think I said 0.15, but my population parameter is 0.11. It's still in that interval. But now we have another sample that's centered at 0.21. It had a sample proportion of 0.21. Well, if I go all the way out to 0.21 and draw my interval and I go 2 standard deviations, is that one actually going to contain my population parameter pi? It's not actually going to contain my population parameter pi. Let's try it and see if we're right here, based off of my not to scale. Right? So if we do 0.21 plus or minus 2 times my standard deviation, 0.021, let's see what that gives me. So 0.21 minus 2 times 0.021 gives me 0.168 0.252. So based on my sample, I think that the plausible values are from 0.168 to 0.252. Let's maybe write that down. So based on our sample data, we think the plausible values for the population proportion are 0.168 to 0.252. Now what happened here is we just happened to get a sample proportion that was really far out in the tails. So we said most of our values should be close to 0.1. It is possible though to get values way out here. It's not super likely, but it is possible. And if we happen to get a sample proportion that's way out in the tail, then when we find our confidence interval, when we find the plausible values based on our sample data, our confidence interval won't actually contain a population proportion. Okay. However, that doesn't happen very often because 95% of all those possible sample proportions will give us a confidence interval that contains the population proportion pi. So like this one did. Really, if I get any sample proportion from about here to here, their confidence interval is going to contain pi, the population proportion. But if I happen to be unlucky and get one way out in the tail, then my confidence interval will actually miss the mark. It will miss actually showing me the population proportion. So this is what you want to remember. 95% of all the possible sample proportions would give us a confidence interval that contains the population proportion pi. But that means that 5%, so 95% and 5%, that ends up to 100. 5% of all our possible sample proportions would give us a confidence interval that does not contain the population proportion pi. Remember we talked about in our test of significance, we talked about possibly making mistakes. So like this number 5 here, this would be like where we made a mistake. Okay, we thought like if we were actually doing a hypothesis test, we're going to say, oh, like 0.11 is not plausible. Okay, 0.11 is not a plausible value for our population proportion, but it actually is. So in this case, we just like made a mistake. We make mistakes when we happen to be unlucky and just get samples that are way out there in the tail. That's how we make mistakes in hypothesis testing. Now, what we can do is we can actually go to a different ISI applet that we haven't done yet. Let me pull those up. When you go to the ISI applets, you can go over here to where it says exploring randomness, and we want to do simulating confidence intervals. And we can simulate what would happen if we took lots of different samples and found the confidence interval for each sample. So we're looking at statistics. You can ignore this binomial model. That's more complicated than what we do in this class. Okay. This is a simulation. We're putting in what we happen to know the population proportion is. We happen to know it's 0.11. We change our sample size to 200. Okay. And right now I'm going to just one interval, and I want a 95% confidence level. So I sample. So let's actually scroll over to the right first. Okay. So in this sample, you can see each individual value, or each of these is like the individual values we got, whether it's a failure or a success. Okay. You can see my sample proportion is 0.115. Here it shows you this is my one sample proportion that I got, and this is the width of my confidence interval. Okay, let's take a different sample. Maybe. Okay, so now I have a different sample. You'll notice my sample proportion is now 0.07. It gave me a different sample proportion and a different width. And now, notice my sample proportion is 0.07 is a really low sample proportion. And if you look right here, so this is 0.11, this is my population proportion. Here's the confidence interval it gave me. Notice that confidence interval is just slightly to the left. It doesn't actually contain my population proportion. Okay. And I can take a different sample. Notice now my sample proportion is 0.115. Okay. I got a different sample proportion, a different width. Notice my confidence interval here. Okay. I was centered at 0.115, and when you look at the confidence interval, it does contain my population proportion. And I could take a different sample, so now I'm centered at 0.080. You can see that when it does the confidence interval, it is wide enough that it does contain my population parameter 0.110. Let's maybe try 10 intervals at a time. So now if I do 10 intervals at a time, you can see these are all the different sample proportions I got. Okay. And these are my different confidence intervals that I got. So each of these confidence intervals is centered somewhere different. Okay, it's centered somewhere different because it has a different sample proportion in the middle. But each of these happens to contain my population parameter of 0.110. Okay. And I could keep taking more samples. So like here's different samples, but notice when I look at my different sample proportions, on one of them, I happen to get a sample proportion that was really low. And notice how it made it red? That's because when you come over here, this confidence interval right here was centered at a sample proportion that was so low that it didn't actually, the confidence interval didn't contain my population proportion. So right now, when I did 10 intervals, about 9 out of 10 of them actually contain my population parameter pi. Let's bump that up to 100 intervals at a time. Okay. So now I got 100 different samples, 100 different sample proportions. Any sample proportions that were kind of here in the middle, they actually give me confidence intervals that contain my population proportion. But anything that's out in the tails isn't going to actually give me a confidence interval that works. It gives me a confidence interval that doesn't actually contain my population proportion. So you can come over here and look at the confidence intervals. This confidence interval is green, it contained it. That confidence interval is green, it contained my population proportion. But anything that's red here, that means I happen to just get a sample proportion that was out in the tails, and so my confidence interval doesn't contain my population proportion. So for these 100 intervals, there were about 91% of these intervals that actually contained the population parameter. But look at my running total. My running total is 93.4%, so I'm kind of close to 95%. And I think if I keep sampling, it will get closer and closer. So now if I look at another 100 intervals, this time there were only 2 that didn't work. So I had 98% of my confidence intervals actually contain my population parameter. But my running total is really close to 95%. Okay, and if I keep going this time, I had 96% that contain my population parameter. My running total is at 95.1. I could do 1,000 intervals at a time. And it's much harder to see, but you can just kind of pick out the red ones here or there where my confidence interval didn't work. And notice I'm at 95.2% of all of those intervals that actually contained my population parameter. And maybe I want to try like 10,000 intervals because we like to simulate at least like 10,000 in this class. Notice out of those 95.1% of my confidence intervals actually contained my population parameter. So the thing with confidence intervals is you never know, am I going to get a sample proportion that's kind of here in the middle that is a good estimate that actually contains my confidence interval actually contains my population proportion? Or am I unlucky? Did I maybe just happen to get a sample proportion that was really far out on the tails, and then the confidence interval doesn't actually go far enough to get my true population proportion? You just never actually know when you take a confidence interval if you happen to get a sample proportion in the middle or out in the tails. So you don't know, did I get a confidence interval that contains my population proportion, or was I unlucky and I got one of those 5% that doesn't work? So I put a screenshot in your notes for you. In this case, I actually happened to do 100 times and I got the 95% exactly. So again, every different sample proportion p hat gives us a different confidence interval for our population proportion pi. But if we look at thousands of possible samples, then about 95% of those samples would give us a confidence interval that contains the population proportion pi. So in theory, so here's some theory things. Okay. It's not actually our theory-based method, but it's just like saying theoretically, this is what we teach you in a statistics class. We can find a 95% confidence interval with our sample statistic plus or minus 2 times the standard deviation of the statistic. So that works for anything we're dealing with. So whether we want to work with means or proportions, this is our general form of our formula. Okay. Now, if you want to talk about proportion specifically, so a 95% confidence interval for a population proportion, pi, well, our sample statistic for proportions is p hat. So it'll be p hat plus or minus 2 times the standard deviation of p hat, standard deviation statistic. But the problem is, what if we don't actually know our population proportion pi? So remember, our standard deviation of p hat, we said our formula is pi times 1 minus pi over n, and then you take the square root. But we don't know our population parameter pi. So how are we going to use this formula to make a confidence interval? That just doesn't really make any sense. You can't estimate pi by using pi in the formula. Okay. So what we're going to do is we're going to estimate it with p hat. Okay. Now we call it standard error. So just like when we were dealing with means, if we have to start estimating the standard deviation, okay, then we call it standard error. So I'll do p hat, our sample proportion, times 1 minus p hat over n, and then take the square root. That's called the standard error of p hat, and it's our best estimate of our standard deviation of p hat. So in general, our 2 standard deviation method, or 2SD method, for a 95% confidence interval for the population proportion pi is going to be p hat plus or minus 2 times the standard deviation p hat. Now, most of the time, if I ask you to do this, you will run the simulation, or I'll give you the simulation and you'll just read the standard deviation off of the simulation. Okay. If you want, you could calculate it by hand. This does take a long time to calculate by hand, relatively speaking, so we're very unlikely to ask you to calculate that by hand on the test, maybe once in a while on the homework. But really, we'll just always be running the simulations, which is why we have this formula. We just read it off the simulation. Now this part, the 2 times the standard deviation p hat, the part that we're adding and subtracting, that's called the margin of error. So that's the part you add and subtract. So you can think of the confidence interval as our sample statistic plus or minus the margin of error. So the part that you're adding and subtracting, that's called the margin of error. We're going to talk about that a lot in this class. We'll ask you, well, what is the margin of error? Okay. Now, as a note here, if we want to run the simulation, let me pull up what the simulation looks like. So if you go to the one proportion applet, it's going to ask you for the probability of heads. Well, that's your population proportion. But what are you going to put in here to run a simulation to find the standard deviation? You can't put in the actual population proportion because you don't know the population proportion. Now, it turns out if you were to run, well, actually, maybe let's just try it really quick. If I was to look at a probability of heads of 0.1, and I take a sample size, it doesn't really matter how big I make this. I draw my samples, I look at the summary statistics, and you'll find the standard deviation is 2.119. Let's look at the proportion of successes, 0.042. Now keep that number in mind. So right now my probability of success is 0.1. Let's see what happens if I change it to like 0.3. So at 0.3, notice now my standard deviation is actually bigger than it was before. It was like 0.04, now it's like 0.06. Let's try 0.5. So at 0.5, my standard deviation is 0.071. Now, if I try like something bigger, like 0.8, my standard deviation actually gets smaller. So it turns out we figured this out through lots of things that we can even show you mathematically. The biggest possible standard deviation always happens when your population proportion is 0.5. So coming back to our notes, pi equals 0.5. Pi equals 0.5 has the biggest standard deviation of the possible sample proportions for any value of pi, or compared to any other pi. So when you're reading a textbook, it'll say, oh, a population proportion of 0.5 has the biggest possible standard deviation. So if we're trying to do a confidence interval and we don't know what our population proportion is, we know that the biggest possible standard deviation happens at 0.5. So if we use that in our calculations for our confidence interval, we'll just get a wider confidence interval. Okay? But we'll be pretty confident that we're correct. We're just a little bit more conservative. Okay? Now, you can do this. I don't ever see anyone do this in practice. Okay, we have fast calculators now. We can just use our actual sample proportion p hat as our best guess for pi, okay, when we run our simulation, and we get better results. So that is in the textbook, that's what they're talking about, but we're just always going to use p hat in our simulations. So we use p hat as our best guess for pi in the simulations. Okay, you could use 0.5. It's more conservative. You get a wider interval. It works, but using p hat as your best guess is going to work better. So let's go back to our example about kissing. So again, remember, Tic Tacs claimed 74% people tilt their head to the right. Guntarkin thought that was wrong. So he observed 80 out of 124 pairs that turned their heads to the right, or p hat equals 0.645. So let's estimate our standard deviation of p hat. So we're going to use our ISI one proportion applet. When I go to use my applet, I need to put my probability of success is 0.645. So p hat is our best guess for our population parameter pi. So we just put in that 0.645. I put in my sample size is 124. I do 10,000 samples. Make sure you click for proportion of success. Make sure you select your summary statistics, and it will tell you that my standard deviation equals 0.043. So my standard deviation of p hat is about 0.043. And that's what all you'd have to do. You put it in the simulation, you read off the standard deviation. Now let's suppose that you didn't have simulations to do it. Let's say you wanted to use the formula. So we don't know pi to actually find the standard deviation of p hat, okay? But we do know that we can just estimate it with our standard error using p hat. So we square root my p hat, what did I say, 0.645 times 1 minus 0.645 over my sample size of 124. Okay. So to put this into your calculator, again, I like to do 0.645 times 1 minus 0.645, don't forget those parentheses. I hit enter, I divide by 124, hit enter, take the square root very last. So 0.04297. Okay, so that's my best estimate of my standard deviation of all the possible sample proportions using the formula. Notice my standard deviation from the simulation, my standard deviation using the formula, they're going to be so similar. You could do it either way. Okay, on the exam, I'm not going to ask you to calculate that because we don't like to see you miss points based on like calculating and putting in your calculator wrong. So this isn't a formula I'll often ask you to do on the exam. I'm much more likely to give you the simulation like this, the simulation results, and you just read the standard deviation off of it. Super simple. That's all you have to do. So let's use the two-standard deviation method to find a 95% confidence interval for the proportion of all the people that turn their head to the right. So we said it's just p hat plus or minus 2 times the standard deviation of p hat. Okay, so our sample proportion was 0.645 plus or minus 2 times the standard deviation, which we just figured out was 0.043. So we'll do 0.645 minus 2 times 0.043. Gives me 0.5592, and now I just do the addition, 0.731. So that's my 95% confidence interval for the proportion of all the people that turn their head to the right. Much easier than testing that like 20 different possible values to see if they're plausible or not. Also much more accurate. I can go out to the thousandths place, 10,000ths, just depending on how you want to round. Let's see, when I look at this interval, what was the center of the interval? Like, where was it centered? So you're always centered at your population proportion. So we're centered, center is always p hat. So 0.645, that's always the middle of the interval. Okay. What was your margin of error? The margin of error is the part that you add and subtract. It's the 2 times the 0.043, which, I don't know what that was, 2 times 0.043 is 0.086. It's just the part that you're adding and subtracting, the two standard deviations, the part that you add or subtract. So the part that you add or subtract is your margin of error. Now, let's suppose that you found a confidence interval for your population proportion and someone told you that it was 0.51 plus or minus 2 times 0.05. Now, this isn't actually super common to see it written like this, but it is very common to see it written as 0.51 plus or minus, let's see, 2 times 0.05 is 0.10. This is very common. You will see it written like this in a lot of research projects. You'll see it written like this all the time when anyone's doing any kind of poll. If you're talking about presidential debates, they'll say, oh, we think 51% will vote for this person with a margin of error of 0.10, or they'll say give or take 0.10. So it's very common for them to report the results like this. Now, just for practice, let's practice labeling each piece. So the 0.51, that's your sample proportion p hat. The 2 is just what we have to do to make the 95% work. And this 0.05 is the standard deviation of p hat. And what do you call the entire 2 times 0.05? That's going to be your margin of error. It's the part you add or subtract. So margin of error means how much do you need to be off by? If you know you're a bit off, you have error in here. How big is that error? That's your margin of error. Okay. If I want to change the interval written like this, though, to actually be written in terms of its endpoints, okay, we just put it in our calculator. So there are problems on the test that are like this. All you have to do is put it in your calculator. So you do 0.51 minus 2 times 0.05 gives me 0.41, and if I add it, then I get 0.61. Okay, and so it's really just write it out, like actually do the calculation. Or you can put it in parentheses like this. So you can write in interval notation, so it's 0.41 to 0.61. The harder thing that we want you to be able to do for objective 4.2.1 is, let's say you have your confidence interval and it's written out in terms of the endpoints. Could you figure out what it was in the p hat plus or minus margin of error? This one is a lot harder. I'm not going to give you a set of formulas that I want you to memorize. Okay, it's just using logic. Okay, so if this is your interval, how do you find the middle of the interval? So first find the middle. To find the middle between two numbers, you basically just find the average of them. So you do 0.23 plus 0.47 divided by 2. Gives you 0.35. So this is the middle. I just took the average of the two endpoints. That's the middle. So that's going to be my p hat. Let's write it like this. So we can say p hat equals 0.35. But now, what's the margin of error? What do they actually have to add or subtract to get there? There's different ways you can do this. Okay. You could say, well, how far is it from 0.35 to like 0.23? So you could be like 0.35 minus 0.23. That gives you 0.12. So the margin of error, the distance from the middle to the end, is 0.12. Or if you wanted, could you have done like 0.47 minus 0.35? It's still going to give you 0.12. So it's just the distance from the middle to the end point. So it could be 0.35 plus or minus 0.12 is how you would write that in terms of p hat plus or minus the margin of error. It's just using logic to figure out what the center was and what the margin of error was. So we learned how to do it by hand using our two standard deviations. But what if we want to use a theory-based confidence interval? Because we have computers, so why do it by hand when we can use theory-based methods? So we can use our theory-based applet to find a one-sample z-interval, confidence intervals first. It's called a z-interval because it's using a normal curve and something called z values. Okay, but that's all happening in the background. It's not anything you have to do. So you go to your eyesight applet, calculators, theory-based inference applet. So the theory-based confidence interval only works if the sample size is large enough, so at least 10 successes and 10 failures. So we'll use our theory-based applet to double-check our 95% confidence interval for the proportion of all people that turn their head to the right when kissing. So let me pull it up and show you. You'd have calculators, you go to theory-based inference, okay. And our sample size, notice, double-check that you're in one proportion. Okay, my sample size is 124. I think we said like 80 people that turn their head to the right. Let's see if I was right. If I click calculate, yep, it's 0.6452. Or if I'd forgotten the count and I just had the sample proportion of 0.645, then I can just put my sample proportion in there and calculate, and it'll figure out, oh, your count must have been 80. Okay. And you can see there were like 64.645 people that said tilted their heads to the right, and 35% that tilted their heads to the left. You can see what was in the sample. You can click confidence interval, and it will automatically do a 95% confidence interval for you, so 0.5609 to 0.7294. So this is my 95% confidence interval. Super easy, super fast to put in our theory-based applet. We can use the theory-based applet as long as we have at least 10 successes and 10 failures. But what if we want another confidence level besides 95%? So what we're going to be doing is we'll have a p hat plus or minus some kind of multiplier times the standard deviation p hat. So for 95%, remember for 95% we did p hat plus or minus 2 times the standard deviations of p hat. Okay, that was how we found our 95% confidence interval. But this 2, that 2 just is related to the 95%. So if we want to do a different confidence interval, we just need a different number there. And so that's why we just said it's like some kind of multiplier times the standard deviation p hat. So we can find what the multiplier needs to be using our normal curve or applets. We have a special name for the multipliers called z star. So for 90% confidence interval, the multiplier z star is 1.645. That's what will give you 90% confidence. For 95% confidence, the multiplier is 1.96. And we've been using 2 because 2 is easy to memorize. So 2 is easier to memorize. But 1.96 is more accurate. Now, that difference is so small, no one's ever going to care. We will keep using 2 anytime we're doing it by hand because it is easier to memorize, okay, and easier to put into your calculator. The computer, though, will just use 1.96 because computers can do that easily. Okay, for 99% confidence, the multiplier is going to be 2.576. So notice that as my confidence level got higher, my multiplier had to get bigger. Okay, the only way you get more confident is to go out wider, okay, to make your multiplier bigger. So the higher the confidence, the larger the multiplier. So this is our nice little formula. It'd be p hat plus or minus the z star, the multiplier, times standard deviation p hat. But again, we're not ever going to ask you to do that by hand if it's not 95% and just the nice, easy memorized 2. This is all what's happening in the theory-based applet. Okay, the computer's doing all of that for us. Again, these values only work when the validity conditions hold at least 10 successes and 10 failures because these values come from a normal distribution. Because the z star comes from the normal curve. And if you don't have at least 10 successes and 10 failures, then your data is not going to look like a normal curve, and so you can't actually use this. Sorry, I said your data, but I meant the sampling distribution of possible sample proportions, won't look like a normal curve if you don't have at least 10 successes and 10 failures. And so these Z-star values that we found aren't going to be accurate. Okay. Again, we just use the theory-based inference applet. We don't have to do any of that by hand. So let's use our theory-based inference applet to find confidence intervals for the kissing data. Remember that n equals 124, p hat equals 645. So we come, again, it's our theory-based applet. We do one proportion. My sample size is 124. My sample proportion is 0.645. I click on confidence intervals. And now I can change my confidence level. So at 90%, I want to calculate it. So it's going to go from, it tells me right here, 0.5745 to 0.7158. On the test, these will usually be written in like parentheses. I like to actually write it out like this because it makes more sense to me in words. Okay. Let's see, let's try 95%. I do find I have to be careful to actually click calculate the confidence interval. Half the time it doesn't actually change. Oh, I guess it did change. 0.5609 to 0.7294 is my 95%. And if I want 99%, click calculate. It's 0.5345 to 0.7558. So easy, so fast. We love our theory-based calculator. Okay, you might wonder, why do we ever want to do it by hand? Because if we have really small sample sizes, we can't use the theory-based, and we're going to have to go use simulations instead. And again, so as we went from 90 to 95% to 99%, what happened to these intervals? Notice my intervals, if you look at these numbers, my intervals got wider and wider as we got higher confidence levels. So higher confidence levels means you have to get wider confidence intervals. That's how you become more accurate. So here's one of my favorite comics because it teaches this lesson. Okay, so we have Garfield taking a look at tomorrow's weather. The high temperature will be between 40 below zero and 200 above. And he says, this guy's never wrong. So if you say you're going to be between negative 40 to 200 is going to be your high temperature tomorrow, are you going to be correct? Yes, you're going to be correct. Like guaranteed 100%, you're going to be correct. Okay. But if I tell you that the high temperature tomorrow is going to be between 70 to 90, you have a much lower chance of being correct. Okay. And so if you want to be more confident, you make your interval wider. Of course, you might get to the point where it's completely ridiculous, but to become more confident, you make your interval wider. One more time, write on your paper, to be more confident, you make your interval wider. Because this will show up on the test, guaranteed. We'll ask you what happens if you change from 95% to 99%. You're like, okay, well, to be more confident, you make your interval wider. Just one more example. As part of the General Social Survey in 2019, a random sample of U.S. adults reported that 881 out of 2,214 said yes, at least one grandparent was born outside the United States. So let's find a 95% confidence interval for the proportion of all the adults in the U.S. with at least one grandparent born outside the U.S. First of all, let's write down what was our p hat. So they didn't tell me p hat. They said 881 out of 2,214. Let's figure out what that is. Looks like 0.398. And also my sample size is 2,214. So step one says use simulation to estimate the standard deviation of p hat. Okay, so when you bring up the one proportion applet, you don't know the population proportion. So what you're going to do is you're going to estimate it with your sample proportion of 0.398. Your sample size is 2,214, and I always like to do at least 10,000 samples. It doesn't really slow me down. Click draw your sample. Make sure you click proportion of successes. You don't have to count your samples. We're not doing a hypothesis test. Make sure you click summary statistics, and it will tell you my standard deviation of p hat, my standard deviation of all my possible sample proportions is 0.010. Now let's try and use the formula instead to estimate it. So we'll do my sample proportion, which we just said is 0.398, times 1 minus 0.398, divided by sample size of 2,214. Let's see, so 0.398 times 1 minus 0.398, divided by 2,214, and take the square root of it. and I get 0.010. Okay. Notice it doesn't matter whether you want to do it by hand or you want to just read it off of the simulation. There's your standard deviation of the possible sample proportions. Okay, so now it says use the two standard deviation method to find the 95% confidence interval. Well, that's just p hat plus or minus 2 times the standard deviation of p hat. So that's going to be 0.398 plus or minus 2 times my 0.01. So let's see, 0.398 minus 2 times 0.01. Oh, you have to type it in correctly. I'm getting 0.378 to 0.418. So that's my best guess for the population proportion, is we're 95% confident that it is within that interval. What if instead we want to use our theory-based calculator applet to find the 90%, 95%, and 99%? Okay, so we open up our applet. I'm going to type in 2,214 for my sample size. And for my sample proportion, I can either put in the 881 people or I can put in the 0.398. You can put in either one and it'll fill in the other one. Hit calculate. Make sure you hit calculate. I often miss that. Come over here to your confidence level. Put in 90%. Hit calculate. So it's going to go from, it looks like 0.3808 to 0.415. And if I change it to 95%, hit calculate, I get 0.3775 to 0.4183. And if I do 99%, hit calculate, I get 0.3711 to 0.4247. Okay. And which interval will be the widest? Well, you can see that the widest one is that 99%. So the higher your confidence, the wider your interval. So 99% is the widest. And finally, let's pick our correct interpretation. Let's remind ourselves of the interpretation. So our confidence interval is always about the population parameter. So it should always talk about the population proportion, or it might call it long run probability. It should never talk about like our sample or another sample or observational units. By that, I mean like individual people or individual whatever you're talking about. Okay, let's try these out now. So we're 99% confident, 39.8% of U.S. adults. That sounds like that's talking about individuals, doesn't it? Individual adults have at least 1 gram per born outside the U.S. So that one's going to be wrong. It's talking about individuals. Next one, we are 99% confident that the proportion of all U.S. adults, well, that's a population proportion, with at least 1 grandparent born outside the U.S. is between 0.37 and 0.42. So that's my population proportion. That one's correct. It's talking about the population proportion. Let's see the next one. We're 99% confident that if we pick a random U.S. adult, again, that's talking about like individuals. So that one's going to be wrong. The next one, we're 99% confident if we pick a sample. Well, that's talking about a sample. That's going to be wrong. The reason we're going to hammer this in is that we find in statistics, people read these research papers and they interpret confidence intervals wrong. We want to make sure that when you read a research paper, you can correctly interpret it.